Thank you very much. Thanks for the invitation and the introduction. So today's talk will be about this conjecture made by Kudla-Rapoport, and the main theorem today will be a proof of this conjecture. So I'm going to start by explaining what the conjecture is and where it comes from, why it is interesting, and then we'll try to explain some ideas of the proof. Okay. So maybe let me begin with something everybody is more familiar, more classical subject of Hurwitz class numbers. So let me remind you, Hurwitz class number is like variant of the usual class number of binary quadratic forms. Okay, so it's a weighted size of the equivalence classes of binary quadratic form of fixed discriminant negative d. Okay, but it's counting not only the size of this equivalence classes, but also encoding the size of the stabilizer of this action. In other words, I'm going to count with these two classes, these two objects with extra symmetry, such as x squared plus y squared. It has an extra twofold symmetry, so I'm counting it with weight multiplicity 1/2. And similarly, for binary quadratic form of this form, I'm going to count with weight multiplicity 1/3. And all the rest don't have extra symmetry, and it's counted with usual multiplicity 1. Okay, so here's our first few familiar example. Okay, for example, discriminant is -3 or -4. You know, the usual class number is 1, corresponding to these two binary quadratic form. And as I said, they are counted with extra multiplicity 1/3 and 1/2. So you get these two Hurwitz class number, H3 and H4. Okay, so this one has discriminant -7 and doesn't have extra symmetry. So Hurwitz class number is equal to the usual class number 1. Okay, so this is more interesting because -12 is no longer a fundamental discriminant. So H12, you see there's one class coming from a scalar multiple of this discriminant -3 quadratic form, and it's counted with weight multiplicity 1/3. And this one is primitive and it's counted with multiplicity 1. So the total Hurwitz class number H12 is 4/3. Okay, and the last one is usual class number for the binary for the quadratic extension Q of adjoint square root of -5, and you know that's everybody learned from their first algebra class. That's the first case where you have class number non-trivial. Okay, it's class number 2. Okay, so you can try to compute the first few Hurwitz class numbers and make a little table like so. I guess one of the central question in classical algebra number theory is to find the patterns between all these Hurwitz class numbers. Of course, we all know that these have very huge amount of arithmetic information. Okay, so it's very unlikely people can understand completely. Okay, but I want to remind you a very remarkable formula of Hurwitz that gives a closed elementary formula for Hurwitz class numbers. Okay, it's not for a single Hurwitz class number, but for a linear combination of Hurwitz class numbers. Okay, so here's a Hurwitz formula. Assume I have an integer that is not a perfect square, m. Okay, so Hurwitz prove the following class number relations. Okay, the left-hand side is what I view as an elementary closed formula. It's taking a summation over all the factorization of this integer m into 2 divisors, and you take the maximum of the dividers. Okay, and the right-hand side, you see, it's a specific summation of various Hurwitz class number, and you are prescribing the discriminant here to be 4m minus t squared, where t rounds over all integers such that 4m minus t squared is positive. All right, so for example, let me give you a simplistic example, m equals to 3, and I guess you have no trouble computing the left-hand side. Okay, this factorization of 3 is 1 times 3 and 3 times 1, so you get 3 plus 3 on the left-hand side. Okay, but the right-hand side is more interesting. It has actually 7 Hurwitz class number for all the discriminant that is a square from 4 times 3, a square from 12. Okay, but I already listed all these Hurwitz class number here, so it's kind of tempting to actually write down, right? Check if this formula checks out. Okay, 1/3, 1, 1, 4/3, 1, 1, 1/3. Okay, so it's a lot of fun to check that it's actually correct. Okay, so I hope this simple example already illustrates how non-trivial Hurwitz formula is, even in the simplest case. it's probably the last way you would imagine to decompose 6 into summation of 7 small rational numbers. Okay, so I want to give you some idea of how Hurwitz proved this formula. But so far, any question about the formula yet? Okay, so here's a picture of Hurwitz. Okay, so maybe you can guess which one is Hurwitz by the exclusion principle. So on the right-hand side, it's Hurwitz's daughter, and the left-hand side, you probably can recognize. That's Einstein, and actually, I find it appropriate to show this picture to you because I find this on the IAS archive for Einstein. Okay, and you can see Hurwitz is not only a good mathematician, but also quite a musician. He's conducting a little band with Einstein his daughter. Okay, so if you look at the 1885 paper of Hurwitz, how does he prove this class number formula? Right, this one. Actually recognize that you find a lot of places he uses function called J. Okay, and I guess modern time everybody recognizes J is a modular J function. So I'm going to try to reformulate Hurwitz's original proof in terms of geometric language, in terms of geometry with the modular curve. Okay, so let me remind you why is this level 1 modular curve, the quotient of upper half plane by SL to Z is also the moduli space of elliptic curves over complex numbers. Okay, so the main player of the proof will be this modular surface formed by a self-product of 2 copies of modular curves, which has a modular interpretation in terms of a pair of elliptic curves. Okay, what is interesting about this modular surface is that associated to any positive integer m, we have natural special divisors associated to it on the modular surface. Okay, so it's best described in terms of modular interpretation. So in order to describe a divisor on the surface, I need to give you an extra condition between the pair of elliptic curves E and E prime. Okay, and this condition is exactly prescribing extra data of isogeny of degree m between E and E prime. Okay, you can see this is a non-trivial condition and it cuts out a divisor on the surface X. Okay, for example, in the simplest case, m equals to 1, and modular interpretation is simply classifying a pair of isomorphic elliptic curves. And so dy is nothing but the diagonal embedded y inside this modular surface. Okay, so we have this now interesting geometric picture. So I have a surface that's quite simple, that's formulated by a product of 2 modular curve. And you know this level 1 modular curve is also isomorphic to A1, the affine. It's nothing but A1 cross A1. Have a diagonal embedded A1 inside this modular surface, and associated to this integer m, I have probably a very complicated divisor on the surface. Okay, but now on a complex surface, I have 2 divisors. You can talk about their intersection number, namely you count the intersection number with 0 with multiplicity. Okay, in the ideal situation, intersection is non-degenerate. It also consists of isolated points. Okay, just add the multiplicity at each of the point and you get a number. Okay, so that's now a curious construction. So I start from an integer m and I construct these 2 divisors zm, z1, and the first step of Hurwitz proof of Hurwitz formula is recognize the left-hand side, this elementary divisor sum is in fact equal to the intersection number of zm and z1. Okay, so I will leave this proof of this formula as a little exercise for you, right? Because intersection theory on A1 and A1, A1 cross A1 is quite simple. Just try to move this cycle to be the diagonal cycle to be essentially a summation of a horizontal fiber and a vertical fiber, and intersection with a fiber, a horizontal or vertical fiber, is clearly related to these divisors. All right, so that's the first step. And I recognize this left-hand side in terms of geometry, 2 divisors on the intersection of 2 divisors on this modular surface. Okay, I want to remark that you see this in geometry interpretation actually give you an explanation of why this assumption m is not a perfect square appeared in a Hurwitz formula. Okay, this exactly ensures that the intersection of these 2 divisors is of expected dimension in the 0 dimension. if M is actually a perfect square, you see actually the diagonal Z1 is a component of Zn, because you can simply take the same elliptic curve and take the isogeny given by multiplication by the square root of M, if M is perfect square. Okay, so in that case, the intersection will be degenerate. Okay, so the assumption is exactly ensure the intersection is non-degenerate. All right, so now in order to prove the Hurwitz formula, I just need to recompute the right-hand side, this intersection number, in a different, possibly different way. But that I can do without doing any intersection theory, without using any geometry of this modular curve. I just do by a modular interpretation. Okay, so modular interpretation is simply counting the number of elliptic curves with a self-isogeny of degree m. Okay, but m is not a perfect square, then this elliptic curve has to have actual endomorphism. So it has to be of complex multiplication, and then you just try to use the theory of complex multiplication to count this, to compute this weighted sum of CM elliptic curves. Okay, and also surprisingly, Hurwitz class number will appear on the right hand side. Okay, so summarize. So I can reinterpret the Hurwitz formula writing this elementary divisor sum as a summation of Hurwitz class numbers by reinterpreting both sides as a geometric quantity, namely intersection number of two divisors on X. All right, any questions so far? Okay, but I guess I'm cheating a little bit because I haven't told you how do I get this particular indices, right? 4m minus t squared, and 4m minus t squared is a positive number. So I would like to offer you a second interpretation of the right-hand side. It seems more natural to explain why these indices come from. For that, I need to use a little bit analytic input. There's a certain relationship between Eisenstein series of genus 2. So let me remind you this Ziegler up half plane of genus 2 consisting of 2 by 2 symmetric complex matrices where the imaginary part Y is positive definite. Okay, so that's a natural generalization of the Euro up half plane. Yeah, but you have now a bigger group SP4 acting on H2. So I can mimic the Euro construction of Eisenstein series GL2 to this case of SP4. I get the Ziegler-Eisenstein series formulated by simply taking this infinite sum. Okay, so like a Euro-Eisenstein series, classical Eisenstein series, it also has a Fourier expansion. And part of the Fourier expansion is holomorphic, indexed by 2 by 2 half integral symmetric matrices that are positive definite. Okay, so I'm going to denote these Fourier coefficient indexed by these matrices by ET, E sub T, ZS. Okay, so if you know a little bit about the theory of Ziegler-Eisenstein series of genus 2, you actually recognize these Fourier coefficients. When you evaluate these Fourier coefficients at s equal to 0, okay, now it's actually a number and it's exactly matching this Hurwitz class number with 4m minus t squared. And you recognize this positive condition on this difference is exactly the positive definite condition on the indices of the Fourier coefficient, where you put n1 on the diagonal and t over 2 on the off diagonal. All right. Now I can reinterpret also the right-hand side naturally as a summation of Fourier coefficients of Eisenstein series, but now on this bigger group SP4. Okay, so now I have successfully reinterpreted a Hurwitz formula, which is kind of a miraculous formula, but now in terms of, on the right-hand side, certain geometric quantity on the modular surface, and on the right-hand side, certain analytic quantity of Fourier coefficients of Eisenstein series on SP4. Okay, but now if I have this interpretation on the bottom, you can see this quantity, of course, exists in vast more generality, so I can try to generalize this formula, much more general setting. Okay, so next I would like to tell you arithmetic generalization due to Gross and Keating. So what I mean by arithmetic generalization? So everybody knows here that the modular surface is X has a natural integral model via the modular interpretation defined over the integers, such that the complex fiber of this arithmetic scheme actually recovers the modular surface. Okay, so because I'm not taking the integral model, this curly x, the integral model, should be viewed as arithmetic threefold. Okay, that's one dimension higher. Okay, but anyway, I can still do a arithmetic intersection theory on this arithmetic threefold. The only difference is that now I need 3 dividers instead of 2 dividers, so that the intersection has the expected dimension 0. Okay, so anyway, I can ask the following question. Suppose I have 3 integers. I have 3 special dividers now on this arithmetic threefold, and I assume the following condition. Assume there's no positive definite binary quadratic form representing these 3 integers simultaneously. Okay, so you can imagine this condition is sort of similar to the condition Hurwitz formula that M is not a perfect square. Okay, so anyway, it's ensuring that the intersection of these 3 divisors indexed by these 3 integers are actually a non-degenerate intersection of exactly expected dimension 0. Okay, so now I can talk about the arithmetic intersections number on the left-hand side. So the question is, is there a similar interpretation in terms of Eisenstein series on the right-hand side? Okay, of course, the first modification to make is that now I have 3 integers. So in order to put these 3 integers on the diagonal, I need a 3 by 3 symmetric matrix. Okay, so instead of the genus 2 Ziegler Eisenstein series, I need to take the genus 3. Okay, genus 3 instead of genus 2. Okay, here, but it's exactly defined by the same formula as the previous slide. Okay, so you would hope that maybe this intersection number is related to valuation of s equal to 0 for this genus 3 Ziegler Eisenstein series. Okay, but you immediately recognize it cannot be true because this arithmetic intersection number is kind of, compared to the geometric intersection number, is a different beast. It has different nature. It's actually a transcendental number. It's a rational linear combination of log p's, where p are running over all the primes. Okay, so the left-hand side is a transcendental number, so it cannot be naively equal to a rational number on the right-hand side. Okay, and even worse, right-hand side, if you check the functional equation of this Eisenstein series, at the center s equal to 0, the functional equation is always -1. Okay, so if you value that s equal to 0, then it's vanishing automatically, always. Okay, so you cannot expect that the left-hand side is complicated arithmetic quantity is equal to 0 always. Okay, but what Gross and Keating discovered is that, well, if the sign of functional equation is -1, it's kind of interesting to take the central derivative, the first derivative at the central point, and miraculously, if you take the derivative and evaluate as equal to 0, then it matches up always. Kind of a miracle identity between these 2 transcendental numbers. All right, any questions about the statement of Gross-Keating? Okay, so now you can imagine, why do I stop at just 3 dividers, right? So here's a vast generalization made precise by Kudla-Rapoport. So this could be considered as a vast conjecture generalization of Gross-Keating formula by replacing this arithmetic threefold now by arithmetic m-fold, namely an integral model of certain Shimura variety associated to either unitary group of signature n-1,1 or an orthogonal group of signature n-1,2. Okay, these particular kinds of Shimura variety are sort of isolated by Kudla because, like this modular surface, it also have a rich supply with divisors. Okay, so these are known as the Kudla-Rapoport dividers, which I denote by ZXI, which living on these arithmetic m-fold. All right, so now Kudla-Rapoport asks, can I compute the now arithmetic intersection of n such Kudla-Rapoport dividers on this arithmetic m-fold? Okay, so the more precise statement is following. Suppose I have a positive definite Hermitian matrix in the unitary case or a half-integral symmetric matrix and positive definite in the orthogonal case with prescribed diagonal entries xi. Okay, then I have these associated dividers on the Rapport dividers on this arithmetic n-fold, and I can ask what the arithmetic intersection number should be. Okay, and they ask, well, conjecturally, the natural generalization on the right-hand side should be the central derivative or Fourier coefficient of certain Eisenstein series, now on a higher rank group. Okay, it's UNN in the unitary case and SP2N in the orthogonal case. All right, for example, if I take n equals to 3, then the split orthogonal group SO22 is essentially 2 copies of SL2. So the relevant Shimura variety in this case is nothing but the product of the 2 modular curve we have discussed. Okay, so in particular, Kudla-Rapoport conjecture would recover the Gross-Keating formula. Okay, I specialize to this special case. And even more, you see now I have no assumptions on these diagonal entries. Okay, I have no assumptions on whether there is a binary quadratic form representing all these numbers. Okay, so it even treats the case of degenerate intersection, right? Because I have no assumptions on these diagonal entries. Okay, but here the Rapoport conjecture hopes that even in a degenerate intersection, after you appropriately define the left-hand side, it should still be equal to the central derivative of the Fourier coefficient of Eisenstein.
What is the analog of the non-arithmetic statement?
Right, that's going to be my next slide. Thanks for asking that. But before that, let me ask, is there any question about the arithmetic statement? Okay, so let me address the question. First one is, there's a non-arithmetic geometric intersection number, but now I'm taking the complex fiber of this Shimura variety. It's a complex Shimura variety of dimension n-1. Okay, so to make sense of it, you have to take intersection number of now n-1 dividers on this complex Shimura variety. Okay, and you replace the right-hand side by a value at near central point for this Fourier coefficient. But now for Eisenstein series on a group of 1 rank lower. Okay, and in fact, that's a theorem of Kudla proved in the 90s. Okay, so it should be viewed as a higher dimensional generalization of Hurwitz formula. Good. Okay, so in particular, if you look at the Kudla's formula, right? So both left-hand and right-hand side are indexed by these matrices T, symmetrical Hermitian matrices T. So you can form a generating series by varying all these T's on both sides. So you can see the right-hand side, I would just recover the value of the Eisenstein series, of whole Eisenstein series. On the left-hand side, I can view the generating series of these geometric intersection number as sort of a geometric analog of Hurwitz theta series. Okay, so you can view now this identity proved by Kudla as a sort of a geometric realization of the well-known Ziegler wave formula. Okay, that is relating an average of theta series on the left-hand side and the value of an Eisenstein series on the right-hand side. Okay, so if I put into this perspective, recognize the Kudla-Rapoport conjecture is part of Kudla's program on the arithmetic version of the Ziegler wave formula. Okay, so now I can form a generating series of these arithmetic intersection number on one side, and this arithmetic theta series should be equal to a central derivative of Eisenstein series on the right-hand side. Okay, and more precisely, this Kudla-Rapoport conjecture is really the non-Archimedean part, right? It's on the integral model over Z. And in fact, there's also the Archimedean part of intersection number, and it should be also related to certain Fourier coefficient of Eisenstein series on the right-hand side. And in fact, this Archimedean part was a theorem proved by Liu in the unitary case, and Yang in the orthogonal case, and in vast more generality by Louis Garcia and the Central. Okay, any question about these remarks? Okay, so I hope to convince you that this kind of identity, conjectural identity, right, relating certain arithmetic geometric quantity and certain analytic quantity should be kind of a deep statement relating certain two words that are kind of different nature. Okay, but if you are a person that is not interested in just generalization for the sake of generalization, so let me also remind you that there's a connection between L functions. Okay, for example, if I take n to be an even integer, then Steve Kudla and Ethan Liu showed that if I have the full arithmetic Zygel formula, and together with the doubling method of Rallis and Piotetsky-Shapiro, now we'll get a relation really called as arithmetic inner product formula. Okay, it's relating arithmetic quantity with the central derivative of the standard L function of certain Caspita automorphic representation on UN or SO to n plus 1. Okay, so that's the standard L function on the classical group on the right hand side, and the left hand side is a certain cycle which I denote by Z pi on the integral model of the Shimura varieties of exact arithmetic middle dimension that is constructed by the method of arithmetic version of the theta. Okay, so you can view this version of this formula relating to the height pairing of cycles on Shimura variety with central derivative L function forms on a classical group as a generalization, arithmetic version of the Euro-Rallis inner product formula, relating Peterson inner product of theta lifting with central value of L function. Okay, so maybe I can also specialize the simplest case n equals to 2. And in the orthogonal case, the split orthogonal group is essentially a copy of SL2, and the arithmetic inner product formula essentially recovers the Gross-Keating formula proved in the 80s. Okay, and these arithmetic theta lifting are essentially Hagener points on the elliptic curve over the rationals, and the central derivative L function on the right-hand side is nothing but the central derivative L function of the elliptic curve itself. Okay, and this Gross-Keating formula, so viewed as arithmetic inner product formula, is proved by Kudla-Rapoport and Yang in certain special cases, and completed in complete generality by Yuan and Zhang in the orthogonal case, and in the unitary by Ethan Liu. So I hope this connection have illustrated that this Kudla-Rapoport conjecture is also intimately linked to the BSD conjecture, and more generally for higher dimensional Shimura variety for Bailinson, Log, and Kartov's conjecture in higher dimensional case. All right, any questions so far about remarks? All right, so here's a summary of what has happened. Okay, so I explained the classical formula of Hurwitz and its arithmetic generalization of Gross-Keating formula. Okay, and those two formulas have respectively generalizations in higher dimension. So for Hurwitz formula, there's Kudla's formula in terms of geometric intersection number, which is a geometric realization of the automorphic formula of Zygel-NOA. And on the arithmetic side, we have the Rapoport conjecture, which is part of the finite part of the arithmetic Zygel wave formula. And via the doubling method, I get the Rallis inner product formula, automorphic world, and the arithmetic analog known as the arithmetic inner product formula, which should be viewed as a higher dimensional generalization of Gross-Keating formula. Okay, so among these 6 entries, you recognize, okay, these two are theorems, classical theorems. These are more recent theorems, and these two are conjectures. Okay, so the arithmetic version of the wave formula and Rallis inner product formula are conjectures. So it's natural to ask if these conjectures are actually true, or is it just our wishful thinking? Okay, so what is known about the Kudla-Rapoport conjecture? So let me remind you, this is formulated almost 20 years ago by Kudla-Rapoport, saying arithmetic intersection number of n arithmetic divisors on Shimura variety should be related to the central derivative of Eisenstein series. So immediately after Kudla-Rapoport formulated the conjecture, they verify the case n equals to 2 as a reality check. They also prove the case of non-degenerate intersection when the intersection of this divisor has expected dimension 0. Okay, in the unitary case, and also recently finished by Bruni-Yang in the orthogonal case. Okay, it turns out that this non-degenerate intersection rarely happens, and in fact, in high dimension, this non-degenerate intersection always essentially reduced to the case n equals to 2. Okay, and the essential step, the next essential step was taken by Turstic. He proved that the Kudla-Rapoport conjecture holds for the next case, n equals to 3. Okay, so let me remind you, this is the case that recovers the classical Gross-Keating formula. And in fact, this first case where the degenerate intersection will happen, and Turstic's formula actually covers, okay, treats all these degenerate intersections as well. Okay, so how do we prove these formulas? Well, this is a precise identity between two numbers. And well, you can just try to compute both sides explicitly, and this is exactly what they have done. Okay, they computed both sides explicitly, involving very complicated formula depending on this matrix T. Okay, but they checked that in each of these individual case, this formula just matches up exactly. Okay, so I highly encourage you to look at Turstic's paper. It's really a tour de force. It's pages of involved the computation. Okay, so you can try to do this, try to use various tricks Turstic used to compute these degenerate intersection. In the next case, n equals to 4. But if you trust me, it's the computation complexity is just growing exponentially. It's very, very difficult to actually prove all compute all the cases in n equals to 4. All right, so the main theorem today is actually the Kudla-Rapoport conjecture holds for all n, okay, without any assumptions. Okay, and needless to say, the proof will be different, will not be by computing both sides explicitly. Okay, I hope I will explain the proof is using the standard tool from local harmonic analysis, namely the uncertainty principle, to run an induction argument on the integer n.
So, excuse me.
Yes.
Do you have a new proof of Gross-Keating?
Exactly. So even in the case n equals to 2 and 3, this proof is different from the case I just illustrated on the top, so Kudla's proof and Turstic proof. Okay, so in particular, if you specialize n equals to 2, it will be a slightly different proof. Okay.
But you say you induct on
Induct
n,
the base.
the base case. So what's a base case?
N equal to 1, which is essentially true.
Okay.
Yeah.
Okay, thank you.
Okay, so I hope I will try to explain this usage of uncertainty principle. But I explained before, now I can combine the Archimedean formulas that is already proven to deduce now cases of arithmetic zero-wave formula in any arbitrary high dimension. Okay, and together with more global inputs, we now can deduce applications to the arithmetic inner product formula for the unitary group, and also deduce certain cases of Bailing-Singh and Bloch's conjecture when the derivative of L function is non-dimensional. The analytic rank is 1. Okay, so this will be appearing in the forthcoming work with Ethan Liu and Wei Zhang. Okay, any questions about the main statements? All right, so now let me try to explain how the proof goes. The first business that's kind of standard in this subject is to reduce this global conjecture to a local conjecture. So this left-hand side, the arithmetic intersection number is defined as a summation of local terms, local arithmetic intersection number. Okay, so via the theory of Peano uniformization, I can reduce this local intersection number to a certain intersection number I denote by int of L, that is certain intersection number on a local Scheme variety. It's the intersection number O and Kudla-Rapoport divisor on a Rapoport-Zink space. Okay, which I hope to define for you later. And similarly, on the right-hand side, the Fourier coefficient of the Eisenstein series should have a factorization when this t is non-singular. So in particular, when you take the derivative, it should be indexed by Leibniz rule. It should be a summation, again, indexed by the primes. Okay, so by a factorization, I can reduce this derivative computation to, again, a local quantity. It's a central derivative of certain local representation density of Hermitian or quadratic forms, which I denoted by partial density on the right-hand side. All right, so if I can do this reduction to local quantities, the question is now, can I equate these local quantities, the intersection number on Rapoport-Zink space and the derivative local representation density? Okay, so next, I'm going to define for you those quantities in a unitary case, which is simpler to explain. Okay, and the goal is to prove this local identity. Okay, so let me remind you this unitary Rapoport-Zink space. Okay, so here's the standard local notation, and fix f over f0 is a ramified quadratic extension of p-adic fields, where the base field has residue field, finite field of size q. This uniformizer denoted by curly pi, and OF forever will be the completion of the maximum ramified extension of OF, and an N will be the unitary Rapoport-Zink space associated with group UN of signature 1 and -1. Okay, so whatever it is, it should be classified in certain p-divisible groups with actual structures mimicking the unitary structure of 1 - 1. Okay, it's classified in certain Hermitian OF modules of that signature within the supersingular quasi-isogeny classes of p-divisible groups. More precisely, it is a formal scheme over the formal spectrum of OF forever, representing the functor setting a test scheme to a collection of quadruples, where the first triple is classifying a Hermitian OF module of prescribed with signature condition 1 and -1 of this test scheme, and the actual data is framing, okay, which is quasi-isogeny between the special fiber of this p-divisible group with the base change of fixed the supersingular p-divisible group over the residue field base change to the special fiber of S. Okay, so the importance of this Rapoport-Zink space is that it provides a p-adic uniformization of the supersingular locus of the unitary Schumann variety at a Kudla inert prime. Okay, so in particular, we know that Kudla reduction should have a smooth integral model. So this Rapoport-Zink space is a formally smooth of the expected relative dimension of -1 over the formal spectrum of ring of integer and forever. Okay, but the geometry of this Rapoport-Zink space is quite complicated. Okay, to illustrate that, first I can compute the reduced subscheme of this Rapoport-Zink space. Okay, it's in fact essentially half dimensionless, n-1/2, take the floor of n-1/2. So you can see that this formal scheme is highly non-reduced. Okay, so there are many directions that is completely formal without physical points, which makes the computation of intersection number quite complicated. Okay, but fortunately, the reduced subscheme we have very good understanding. Namely, this reduced subscheme has a so-called Brouillard-Tisse stratification into certain smooth projective varieties, okay, of dimension from 0 to this top dimension n-1/2. Okay, so each of these strata looks pretty concrete. It's a generalized Deligne-Lustig variety of dimension I associated to a parabolic subgroup of finite unitary group of 2i + 1 variables. Okay, so these strata, these generalized Deligne-Lustig varieties, sort of intersect in a very intricate way, mimicking the Brouillard-Tisse building of the p-adic unitary. Okay, so without telling you sort of all the technical definition, let me just give you 2 examples to illustrate the geometry. For example, if you take n equals to 1, and 1 is a relative dimension of 0, so this exactly is the formal spectrum of a ring of integer, and the reduced scheme has dimension 0, it's consisting of a single point. Okay, so in this case, very simple. So n equals to 3, now you have Rapoport-Zink space of relative dimension 2, but now you only have reduced the scheme of 1 dimension. Okay, so here's a geometric picture. On the generic fiber, I have certain rigid surface, dimension 2. On the special fiber, I have a distinct locus, a 1-dimensional locus, given by the reduced subscheme. Okay, so it's quite an intricate combinatorially of a bunch of curves intersecting at points. Okay, and these 0-dimensional structure are just consisting of single points, and 1-dimensional strata consisting of the Fermat curve of degree q+1. Okay, and you can also compute these quantity, the combinatorial structural constants, q+1, the linguistic curve intersecting at a point, and at each, okay, and each the linguistic curve, there are exactly q+1 points on it. All right, so now I can define this arithmetic intersection number using the analog of Kudla-Rapoport dividers. Okay, so let me take a non-split Hermitian form of dimension n, denoted by both v. So this each vector in this Hermitian space can be viewed as a special quasi-homomorphism of p-divisible groups. Okay, so in particular, you can require an extra condition of requiring this special homomorphism, quasi-homomorphism, to deform to an actual homomorphism between the p-divisible groups. And that's one extra condition, and define a divisor on this Rapoport space, which I denote by Zx. Okay, so by the modular interpretation, you know, this divisor is non-empty only when this vector is integral, namely the norm of this vector is in the integer green. Okay, so now I can take n dividers. So let's take OF lattice of rank n with the basis x1 through xn. I'm going to define the Kudla-Rapoport cycle simply by intersecting the n dividers associated to the basis. Okay, so in general, this intersection will not be degenerate, non-degenerate. It probably have higher dimension than you expected. So the good way to define the arithmetic intersection number will be doing a derived intersection. So the intersection number associated to this lattice will be taking the Euler characteristic of the coherent sheaves, this structure sheaves associated to these dividers. Take a derived tensor product, I get a complex sheaf, and take the Euler characteristic. Okay, and this derivedness, this higher tau term will be needed to treat the degenerate intersection with this degenerate intersection number more well behaved. Okay, but in any case, associated to lattice, I get an integer, that is the arithmetic intersection number. And moreover, you can show that this intersection number depends only on the lattice and not on the choice of the basis xi through x1 through xn. Okay, and again, by this modular interpretation, this arithmetic intersection number is non-zero only when the lattice is integral. Okay, so again, let me give you one of the simplest example of degenerate intersection. So let me take the lattice consisting of 3 basis vector. Each of the vector is has norm p, norm pi, the uniformizer. Okay, so the associated Kudla-Rapoport cycle, the intersection of these 3 dividers, okay, in fact, it is not of expect dimension 0, it has dimension 1. It's the simplest case of degenerate intersection. Okay, it's in fact exactly isomorphic to the linguistic curve. Okay, this Fermat curve dimension of degree q+1. Okay, you can also compute this intersection number, the integer, and in this case, it's equal to the Euler characteristic of this linguistic curve. Okay, but there's a plane curve, so I have no trouble to compute this Euler characteristic. I plug in the Euler characteristic formula, right? It's given by this number, 2 plus q minus q squared. Okay, keep in mind this number. Okay, we may need to encounter this again later. Okay, but anyway, you get this random number here as the intersection associated to the simplest Hermitian lattice, where the 3 basis vectors are of norm pi. Okay, so I have finished the discussion of the arithmetic side. this intersection number. Now let me come to the analytic side. Okay, so to define for you the local density, let me take two Hermitian OF lattices. I'm going to define a scheme of representations of one of the lattice M by the other lattice L. Okay, so roughly speaking, I'm looking at the possible homomorphisms from L into M that are also preserving the Hermitian structure. Okay, in other words, for any OF scheme such that it's an OF scheme such that for any OF0 algebra R, the R points is given by this set of Hermitian module homomorphisms. Okay, and the local density is trying to measure how large the scheme is, how many different ways I can embed into L into M. Okay, of course, this doesn't literally make sense, but I can always talk about the local density of the scheme. Namely, I can count how many points of this scheme have over these truncated rings. Okay, that's actually a finite set, so I can count the number of elements. Then I renormalize this counting by the dimension of this generic fiber of this scheme. Okay, I take the limit for the truncation to go to infinity, and this density will converge. That's the local density of M representation of M by L. Okay, so let me give you again simplistic example. If I take two self-dual lattice of rank N, then this local density is computed as this simple number. And as you can imagine, this is exactly recovering the local Tawagawa number for the p-adic unitary. Okay, and similarly, I can change my bigger lattice M to be slightly bigger rank M plus K, then get a slight variant of the local Tawagawa number. Okay, it's variation of this polynomial at x equal to minus q to the minus 2k power. So in particular, when k equals to 0, you recover the previous. Okay, so what you observe by doing this computation is that, well, if I vary the first factor to be a self-dual lattice of increasing ranks, then this density, local density, is in fact a polynomial in this variable minus q to the minus k with rational coefficients. Okay, in fact, you can do a little bit better by renormalizing. Okay, take this polynomial and renormalize this factor. Okay, appeared on the previous slide, then I get actually a polynomial with integral coefficients. Okay, it's really called the normalized Ziegel series. Okay, and it's playing a central role of computing the Fourier coefficients of Ziegel-Eisenstein series. And therefore, there's a vast literature on computing explicit formulas for these normalized Ziegel series. Okay, especially work of Chou, recent work of Chou and Yamauchi is particularly useful for us. Okay, so it is known that the local density, this normalized Ziegel series, this integral polynomial, has actual symmetry. Namely, it says a functional equation replacing x by 1 over x. And the sign of functional equation is exactly given by the valuation of this lattice. Okay, in particular, if the valuation of the lattice is odd, then I get the final functional equation is exactly minus 1. If the central value of this normalized Ziegel series vanishes. Okay, and in this case, naturally, I will consider the central derivative of the local density. Okay, at the central point x equals 1. Okay, so that finished the definition on my right-hand side. Okay, you can see this is a purely analytic quantity that I can construct, okay, for any Hermitian lattice L. Okay, maybe let me just give you another simplest example. In this case, L is a rank 3 lattice with basis of norm pi. Okay, so if you just plug in the explicit formula due to Chou and Yamauchi, okay, you get this integral polynomial. Okay, the first factor is quite simple. And second factor is already slightly more complicated, and you see this QQ plus 1. That's already related to this Rapoport-Zink split. There's certain structural consistence of the Broughton's tree in this case. Okay, but if you just write this polynomial in this way, it's not obvious at all that this polynomial has actual symmetry, right? Anyway, I can write it out. Okay, and you see now there's actual symmetry reflecting the coefficients, okay, between, okay, the symmetric terms. Okay, so in particular, it satisfies the functional equation with sign of functional equation -1. Okay, so in this case, it's meaningful to talk about the central derivative of this local density. Okay, but I have this cubic polynomial. I just compute its central derivative at x equals 1, which probably can assign to your calculus students to do in their midterm. Okay, so you get this number, and if you simplify it, you get the same number that, if you remember, right, this same number that appeared as the Euler characteristic of the Deligne-Lustig curve. Okay, which is nothing but the intersection number associated to this lattice. Okay, so in some sense, it's really a miracle, right? This purely analytic quantity knows about the Euler characteristic of the Deligne-Lustig curve in this situation. All right, any questions so far? Okay, so the general conjecture is that it's not only a special case. It's true in complete generality. If I take L to be an arbitrary rank n lattice inside this Hermitian space, then these two quantities are always the same. Okay, and the May theorem is really the key crucial theorem is that this local Kudla-Rapoport conjecture holds. Okay, for arbitrary rank n lattice. All right, now let me try to explain the proof strategy of this local statement. Okay, so it's going to be an induction argument on n, and the starting point of this induction is quite fairly simple observation. Namely, if I take a vector inside this Hermitian space with valuation 0, in other words, the norm of this vector has is a unit. It has unit norm. Okay, so the observation is that if I have a unit norm vector inside a Hermitian lattice, then the Hermitian lattice can be split as an orthogonal direct sum of this unit norm vector x and its orthogonal complement. Okay, that's very special for unit norm vector. So that decomposition reflected in geometry is saying, okay, if I take a unit norm vector and look at the special divisor, the Rapoport divisor associated to x, I get some dimension n-1, okay, one divisors inside the dimension n Rapoport-Zink space, and in this case, it's nothing but the rank n-1 Rapoport-Zink space. Okay, so I can realize Rapoport-Zink space of dimension n-1 as a divisor of unit norm inside the Rapoport-Zink space of dimension n. Okay, so this is the key to reduce the problem to one dimension. Okay, so I'm going to do the following construction. I'm going to fix the first n-1 vectors. So take a lattice denoted by L flat of dimension n-1. Okay, so I'm going to consider a lattice that is given by an orthogonal direct sum of L flat and unit norm vector, valuation 0 vector x. Okay, so then by this observation, I get a relation between the intersection number on the rank n Rapoport-Zink space and the rank n-1 Rapoport-Zink space. Okay, they in fact are equal to each other. Similarly, I can run the same argument on the analytic side as well. The local density, its derivative, is also related as long as I take the lattice to be of this special form. Okay, the lattice also only direct sum with a unit norm vector. Okay, so now let's apply the uncertainty principle. So again, I'm going to fix L flat such that the span of this n-1 rank n-1 lattice is it's a hyperplane that is non-degenerate for this Hermitian space. Okay, so now I'm going to define functions by varying the last vector. So we fix the first n-1 vectors and vary the last vector. Okay, so that's a lattice in the rank n Rapoport-Zink space, and it makes sense to talk about the intersection number. Okay, so this intersection number will be a function on the last vector x. Similarly, I get a function on the last vector for the analytic side as well. Now, by induction on n, suppose I take the difference function of this intersection function and this analytic function, the partial density function. By induction on n, I know that if x has valuation exactly equal to 0, then they are equal to each other. Namely, the distance function will vanish on the set of vectors has unit norm. And moreover, if the valuation of the vector is strictly smaller than 0, then the lattice is not even integral, right? So as explained, if the lattice is not even integral, then both sides are 0 automatically. So it is also agreeing. Okay, so the difference function will also vanish if the vector has strictly less than 0 valuation. So in other words, by induction n, I already know the difference function vanished on a very large set. All right, what we decide to prove is that this difference function, in fact, it vanishes identically, okay, without any restriction on x. All right, so now where we use the uncertainty principle. So let me remind you, if I have a Schwartz function, a locally constant and compact support function on this Hermitian space, satisfying that both the function itself and its Fourier transform phi hat vanish on this very large set, namely the vectors of valuation smaller than 0, then the function itself has to be 0. Okay, so in other words, it's saying the function phi itself and its Fourier transform cannot have very small supports simultaneously unless the function itself is 0. Okay, but I already have a control of the support over my original function phi, so it remains to control the support or the Fourier transform for the difference function phi. Okay, so if I can compute the Fourier transform phi hat and also know a little bit about its support, then I will win by uncertainty principle. Okay, but it's not that simple, because we recognize that both the function, this intersection function and this local density function, are not even Schwartz. They have singularities along this hyperplane spanned by the first n-1 vector, right? So if you take a vector that is approaching to the hyperplane, more closely, you imagine the intersection number becomes bigger and eventually blows up. Okay, so it's even not, it's causing trouble in computing the Fourier transforms and even showing that the difference function is in fact a Schwartz function. Okay. Any question about the strategy so far? Okay, so yeah, summarize, I created two functions on the Hermitian space, and I already know the function has very large support. And in order to prove that function is identical to 0, I just need to control the support of its Fourier transform. But the issue is that the Fourier transform is not easy to compute because the function itself may have singularities. To solve the problem, okay, so I need to isolate a singularity, okay, and its solution is given by the following decomposition. Okay, so I'm going to decompose this intersection function into two parts, the horizontal part and a vertical part. Okay, and it's geometrically quite clear because I'm taking a lattice of rank n-1, so the intersection of n-1 divisor, so the expected dimension should be 1. Okay, but in general, of course, the intersection could have higher dimension, but because my Rapoport-Zink space only have one dimension in a horizontal direction, okay, I isolate the correct intersection in the horizontal direction, which I denote by this horizontal part. Okay, so the vertical part may be more complicated, may have higher dimension. But anyway, I can define the horizontal part of the intersection number by taking the horizontal component of this intersection, ZL flat, and I do a derived intersection with the last divisor. Okay, and the vertical part will be the remaining piece of the intersection number given by the total intersection number subtracted by the horizontal contribution. Okay, so the hope is that we can understand the horizontal part quite effectively and control the singularity, and the vertical part, of course, now I can reduce to a algebraic geometry problem over the residue field, and hopefully have more tools from algebraic geometry to deal with this horizontal component. Okay, so by the uncertainty principle and the induction hypothesis on N will be done if we can prove that, first of all, I can identify the horizontal part from both geometric side and the analytic side. Right? And second, if I remove the horizontal part, namely the vertical part remaining is actually having no singularity, just Schwartz function, and I can compute to the Fourier transform, it is essentially invariant. Okay, it's invariant up to the sign. And similar statement holds for the vertical part of the analytic side. It's also Schwartz and essentially invariant on the Fourier transform. Okay, so I guess you would agree that if I can show this P theorem, then I'll win by uncertainty principle, because I subtract the singularity and remaining a Schwartz function, and it's invariant essentially on the Fourier transform. So if I know the support of my original function, I also have control over the support of the Fourier transform. Okay, so it's essential to understand, right, this extra symmetry that is really helping me to control the support of the Fourier transform. Okay, so where does this extra symmetry come from? Well, it's not so surprising, because this invariance on the Fourier transform can be really viewed as a local analog of a modularity result proved by these people for generating series of arithmetic divisors. Okay, but for the proof, we are actually not using this global statement. The proof is completely local. So let me finally finish by describing the ingredients of proving these three statements. Okay, so the first one is to explicitly understand the horizontal part of the Kudla-Rapoport cycle. And we actually described it explicitly in terms of gross quasi-canonical lifting cycles. Okay, using the deformation theory of p-divisible groups. Okay, so it's very explicit that I can match the horizontal part of the local density side explicitly as well. Okay, for the second part, to prove the vertical part is actually invariant on the Fourier transform, we prove the Tate conjecture for generalized Delilustic variety appearing in this Buhatit-Strata mode Rapoport space. It is a homological computation of Lustig back into the 70s. Okay, now if we know the Tate conjecture, we know the Tate cycles on these Rapoport-Zink space will be a linear combination of Delilustic subvarieties. Okay, by moving cycles. Okay, Tate cycles will be a linear combination of cycle classes of Delilustic curves, in fact. Okay, therefore I can reduce the intersection of the vertical part of the computation to the concrete problem of intersection with Delilustic curve and the divisor Zx. And evidently, that's much easier computation, intersection problem to compute. Okay, and we compute this function explicitly, and you can just see explicitly that this function is invariant on the Fourier transform. Okay, and finally, on the analytic side, this Fourier transform, of course, will be related to the functional equation of the local density function. Okay, and we use extensively the recent formula of Chao and Yamauchi in terms of explicit lattice theory, and use a functional equation for these local density functions. Okay, so combining these three, I can prove the key theorem, and by induction, we prove the local Kudla-Rapoport conjecture. Okay, thanks, and thanks for the attention, and stay safe, please.
Other question for Chao?
You just mentioned you have something for the realistic interpreter formula. What exactly proved?
Okay, so there are two parts of the statement. One is an application for the Billings and Bloch conjecture. So suppose I have certain automorphic representation on the quasi-split unitary group of dimension 2n. And suppose the analytic rank of the L function associated to this automorphic representation is 1. Then we can show that the Chao group of the associated Shimura variety localized at the Heck algebra, the maximum ideal associated to this automorphic representation is non-trivial. Okay, so that's the first part. The second part is assuming the modularity result for the generating series of codimension arbitrary codimension cycle on this Shimura variety, we can verify even Liu's conjecture made in his thesis. Namely, there's the natural Bailenson height of this arithmetic theta lift is equal to the central derivative of the L function, the standard L function of these automorphic forms, up to explicit local factors.
I have a simple question. Say, go back to the Gross-Keating case where there's a lot, you have to compute Green's functions at the Archimedean place.
That's right.
So you haven't discussed that at all. Is there any issue there or is this not that aspect?
Of course, that needs to be done, and it's a theorem of Liu and Garcia, Sankar, and Green and Young. They compute the Archimedean formulas already.
I see.
Yes.
But it's for orthogonal case, it's a Wei-Zhan.
The Ziegel-Wey formula, the point is, I guess I'm trying to understand even something much more basic. The fact that at what point in the arguments, at what earliest point is it become clear that the derivative is a period or some transcendental thing times something algebraic for the derivative in this generality? You understand my question?
So maybe I'd go to this remark. Okay, so maybe you are talking about this formula.
Yeah, okay, yeah.
So the central derivative of this L function or automorphic form is related to certain transcendental number. It's height pairing of certain cycle. Did I understand your question?
Yeah, I'm trying to understand where these things are married. You're just doing local computations.
Yes. So the height
said
pairing.
that various quantities factor into product of local things, right?
That's right.
Which is why at all but the Archimedean place, you're computing and comparing factors.
That's right.
What's happening at the Archimedean place? I guess that's what I'm asking.
Yes. For the arithmetic Ziegel-Wey formula, there are also Fourier coefficients contributed.
I guess let me just put it this way: you have a new proof of Gross-Keating.
Yes.
Do you avoid computing Green's functions in your new proof?
No, no.
Okay, so that's I'm asking. Where is it in your proof? Or
So
are you quoting somebody else's?
The Gross-Keating formula, of course, they are consisting of both non-Archimedean computation and Archimedean computation. I'm saying the non-Archimedean computation, now we have a different proof.
Okay, that was my question.
Yes.
Fair enough.
Yes.
I'm happy.
So what do you mean you have a new proof of Gross-Keating?
Meaning that this induction argument, right? This local computation is a different computation. It's an induction argument reduced to
the intersection part, yeah.
Yeah, the intersection part, the non-Archimedean computation.
Yeah.
Oh, you mean the Gross formula?
Yeah.
Right.
So it's not really nothing to do with Zagi.
Right, Gross part of the Gross-Keating. Yes.
Okay. So, okay, so I went back to this, when you say this Placato, so there's a Rayleigh's inner product formula. One side is error function of I have a two unitary group, right? Split unitary group, right?
Yeah, quasi-split unitary group. Yes.
Quasi-split unitary group. You have error function. Then there. Okay, so your slides then that it's a really even Liu is a conjecture, right? Unitary
Yeah,
case
conjecture in his form.
He says it. So you said that you can show that if the derivative non-variation, then the Selmer group is of rank 1.
The Chao group localized at the maximum ideal Heck algebra is non-trivial.
Chao group is the maximum. Heck algebra is non-trivial.
Yes.
So okay, so you don't really. I mean, this is unconditional.
Right.
That's nice. So you don't really worry about how the height is defined. Okay, so this look like, okay, this is a qualitative result, right?
Yeah.
So you want to get a quantitative result, then you need a modularity.
You need modularity. It's still not known in the unitary case.
In the modularity, in only the generic fiber or your modularity?
Ungeneric fiber. Ungeneric fiber.
A generic fiber.
Yes.
Okay, okay. So you don't, what kind of assumption you have there and the Shmurov right itself? You don't need
of course, there will be a quite restrictive assumption at inert places because the level of this Shmurov have to be very mild. It's
very
either
small.
hyperspecial level or a certain special paraphoric level. Otherwise, the integral model have problems, right? We don't have even regular integral models to make sense of this.
Do you actually prove some kind of version of arithmetic Zigorvei? Or okay, so right, so you still assume that there's no coherent part. How do you distinguish two parts, right? And usually, the arithmetic Zigorvei cannot even formulate if there's a coherent part there.
Right. So this version of arithmetic Zigorvei formula, we are actually working over the integral model. So we choose a particular integral model.
Okay.
So for the integral model we chose, in fact, there is no ambiguity about the coherent term. It's literally true. It's literally identity between the derivative.
Okay.
There's no coherent term at all.
Yes, I always worry about it when people are.
Yeah, but of course that's a legitimate question to ask. What happens?
It's not a. I don't believe anybody actually even formulate what should be called a arithmetic Zigorvei.
Right. Agreed. Yeah.
Okay. Thank you.
Excellent.
Are there more questions?
Why is it relevant to prove the Tate conjecture for these linguistic varieties?
Because, as I said, you see these cycles on the special fiber are quite complicated. So how it could be a generally very complicated variety. I don't know how to compute this intersection number with an arbitrary variety inside the special fiber. Okay, but the net result is that I can compute the cycle class. All of these hypothetical cycles, right, probably have degenerate intersection to be a linear combination of Tate classes, because we proved the Tate conjecture for this linguistic variety. And even better, this Tate conjecture is proved by exhibiting explicit cycles. And they have to become from the linguistic variety of smaller dimension. Okay, then the intersection problem with this explicit linguistic variety now is a concrete problem, can be solved directly.
All right, so if there's no more question, I'm going to unmute everyone and let's.
Yeah, I can. One more question.
Okay.
When will your work with Yifan Liu and Wei Zhang be available?
Hopefully soon.
How soon?
I don't want to say a date.
Okay.
Sorry.
Okay. Unmute everyone.